Alright, welcome back to the MCA algorithm. So today we continue what we taught last video. So before we jump to the MCA algorithm, so let us say happy Friday to everyone. Today is Sunday with the nice weather. I'm sure we had a lot of outside activities like uh, go fishing, barbecue, drinking, something like that. But don't drink too much, okay? So, but I always encourage people to do something new every day, learning something new every day, and sharing with others. Show how you can do that, okay? And teaching everybody, okay? So that's my goal of the channel: learning, sharing, and growing. Okay, go back to the lesson. So we already know the basic of how particle filter work. So today uh, we will continue with the algorithm in the C++ code. So in the C++ code, we will have several steps right here. The first one, we have the motion and sensing of robots. We have as a noise in the environment. We have the generate particle filters in the environment. We add important weights into particles, and after that, we resampling the particle for every iteration, right? So, and after that, we had to calculate the error, your result, okay? And the last step, we wrapping to see how it look like, right? So the first thing in the code writes in the class. So you have the robot class code, and you just try to learn how to run the robots turn right, turn left. Okay, in the environment right here. Okay, we have environment 100 meter and 100 meter with the A landmarks right here. The dot, red dot right here is the landmark. Okay, and robot can move forward, left, right. Okay, in this map. Not only that, the robot also has the position S, Y, and orientation. Okay, and in the robot they have the functions sense. It means they utilize the sensor to measure distance from the landmarks to the robot. Okay, every movement this value always update how they measure how far from the landmarks to the robot. In the generate particles, we have the map right here, 100 times 100. So we generate about 1000 particles. Okay, that's green dot right here, particle entirely map. You generate 1000 particles entirely map. Okay, right here. It's particle right here. They have the S, Y, and orientation. S particle, Y particle, and orientation particle. So not only that, in this environment, they have the noise. They have forward noise, turn noise, and send noise. So look like last video I already showed you how the algorithm MCL work. They have the two main loops right here. The first one generate the particle, add the weight to the particle. The second one you resampling the particle. Okay, after every iterations. Right here you can see the noise we can add to the code. You have forward noise, turn noise, and send noise. Okay, add to the particles. Okay, and the one more thing I want to mention right here, that's important ways, how we add the important ways into the particles. So we know the robot can sense. I mean, they can measure to landmark, A landmarks right here. They can measure distance. Every time they move into this map, they can get the distance from the robot to the landmarks, right? We also know one more values is the distance from its particle into the landmark. It's the predicted the measurements. Okay, so the difference between the actual measurement z and predicted measurement for each particle right here, we got the important weight. Right, this value will add into the particle. Here, the whole picture of pre-sampling process. We have the end particles. Okay, we generate the end particle. The first step, we each particle they will have the s, y, and rotation for each particle 1, 2 to n, right? After that, we add the weight into each particle, right? And we sum the weight right here. Okay, in the code we do the same step right here. Okay, after that we normalize the way we calculate the probabilities of each particle, the small one divided to sum up of them right here. Okay, so displacement right here you have the after we have the n particles in this group. Okay, so after resembling n times, we only choose the larger probability of each particle right here. Okay, and for example, in the picture, you can the wheel, resemble the wheel right here. They have the 8 particles, right? Each particle they had a weight. For example, two small one particle they had a weight, and with the smallest weight right here, the W1 and W3, right? They have a 0.6 or 0.6 and 1, 3. But the largest one is the 4 and 7, right? Particle 4 and particle 7. So how the resembling wheel, how they can filter. It means they choose the highest one, highest property of a particle. Every resembling process, okay, happen. Here is the pseudocode resembling wheel. For example, we have right here we have the 8 particles with different weights, right? So we run the log from 1 to 8, and for its initial value we say beta equals 0. So for example, we start at the weight 6 right here. So beta will be 2 times the maximum weight right here is a 4. We had a beta at 2 times maximum weight. So the values, the first one from here to here, right? So right now we start at the W6. The value of W6 right here, the weight rate is smaller than beta, so we continue use the beta minus 2 W6, the weight right here, the weight of W6 right here, right? So we also have this value, and after that we increment the index right here. We continue index 7, right? In index 7, you see the weight 7, they have the beta right here smaller than W7. So this condition is 4, right? So we got the select the value W7. That's the whole code resembling wheel code right here. You can see, and you can see right here. Okay, we're in the for loop 1 to 8, and you and the beta right here. Go beta plus 2 times W mass. Mass is right here, for example 4. And for example, I give you specific example when if they start at 6 right here, weight 6, and they apply this condition at WS6 is less than the value beta right here. So we continue right here minus 2 W6, and we have the value beta right here, new value beta right here, and we increase the index value to 7, and it's 7. You see this condition is wrong, so we select the p index as 7, right? And we continue the loop again. That's the resembling process, right? So after this one, I jump to the code right now, but I want to tell you when you have to calculate the error. It means you need to compute the average distance between each particle and the robot. I mean, they have a function to evaluate the overall quality of your solution. Okay, let's see. How you understand the resembling wheel right here and how it's work. For the code, the C++ code, I give you the link and you download it. I encourage you play the code into the Linux system because the code will show you the plots, the graph. But right here, the graphs use the library, the matplotlib library, I mean from the Python, the link to the Python. So if you use the Visual Studio, I don't know it's what or not, but you use in the Linux system, it will be work. Because you have to include up the Python library into the C++ code. We in this code we already have the class robot, and right here you create the landmarks. Right here you can see the landmark, the red one right here. Okay, the red one right here, the coordinate system of the landmarks right here. And so you have the word size 100 times 100, right? And in the class robot right here, you also have some the function of the robot, set robot right here. It means the new position and orientation of the robot. You have the set noise. You can call the set in the main, just call this function and just add the value into the function. Okay, send measurement differ from the landmark to the robot. Okay, the moves we say turn robot how much and forward robot how much. You just add call into the main function. Okay, and so suppose print out the value of both the current position of the robots. Okay, and reach sensor they will print out the value of the sensor. How they measure from the robot to the landmarks. Okay, I mean in this class they already all the function you need. The important thing right here, how you use this one into the main function. How we apply the MCL algorithm into the function, because here's a visualization. So how we understand the MCL algorithm into the main function right here. The first time you can practice play with the glass robot right here. You say I want to set the noise right here, how much value you want. I want to set call the glass robot right here, and we put the name class, new class in my robot, and we put call the function of the class move robot counterclockwise or pi power to 90 degree and moving forward 15 meter. It means right here you can change this value whatever you want, and you can see I'll bring out this value to see how it look like, right? And that's practice to familiar with the code. And the second one, you start apply with the code with MCL in the code right here. You call I want to generate the particle is 1000, right? 1000 or particle right here. And you see, and you run the for loop, and you can, for example, right here you can, okay, you can see that do one small some sample of the class robot and see how it's work. You see, they will print you the value of the 1000, the value as y and orientation as y and orientation for okay, right here you say I want to create the noise right here, the says the particles right here 1000, they print out something like this. You can see how the value right here, see our value to see how it look like in your code. Okay, and right now we come to the code. Right here I want to when you read the code, you see the visualization function right here. They use the matplotlib from the Python. You have to add the matplotlib cpp.h right here into right here. In the Python, you can we already saw this one library. So in the C++, if you want to know how they use Python in C++, take one more step. You have to add it on. Okay. Just a visualization, you just the same Python code. You can want to see the landmarks, the robot's position, the landmark, the particle. You just draw the particle in green right here. These coordinates of the particle. That's coordinate of this the green one is mean the host particles. The resemble, after resemble is we put into the yellow one, and landmarks right here is the red one. Just put the value right here, and you plot the robot's position right here. Okay, and after all the, because we iteration about 50 steps, so to see how the resampling process happen, how it look like, converts the value or not. So we save the picture into this folder image. Okay, right here the folder is empty right here. So in the main we will generate the particle. Okay, right here, you understand? You create the vector z right here as the measurement. You but start iterate 50 times over the particle. Okay, you run the for loop right here. You see, right here you will move the robot and send environment. Okay, you say move on 1 and 5, and you put the measurement into z vector right here. Okay, and continue. We add the motion for each particle. Okay, each particle they have the sy and orientation too, right? As value into b2. We generate the particle weights depend on the robot measurement right here. Okay, we add the weight into each particle, and after that, resampling particle with, you remember, with the same properly proportion to important weight. So we do the same algorithm. You see, the beta more than index, so the beta minus 2w index, and after that you increase the index. Okay, you select the that's index, right? That is one iteration. Okay, and right here, and the last one here is evaluation error. They calculate the difference between the robot's position to the particle position. Okay, how different see, and right here is visualization my robot. Okay, that's how look hard to see. You call the app, this is the name in the executive file you want to run. Something wrong. Something wrong. Let's see where. Sensor. PLT 202 in the plus function. Okay, I forgot the namespace PLT right here. Okay, they create the executive file right here, you can see, and in this one just say R. Okay, right here they will run 50 steps per iteration. You see, you need to evaluation function right here to compute the average distance between the particles and the robot. And a good solution will result in average distance smaller than meters. they had to run from 1 to 49, 0 to 49. We asked them about 40 or 50 steps. So every step they resemble the particle, okay? So you will see in the pictures the particle will resemble. It means they will some futures, some particle with this lower is more probability of survival will die, and the particle have the high probability. Okay, 49, 2 more. You can see the evaluation rate between the average distance between the particle and robot rate is 1 meter. Okay. Okay. Let's see. So you have a bundle of the picture from step 0 to step 49. Let's see how it looks like for each step. Step 0, you can see we generate 1000. Okay, we generate 1000 particle, and after the first several resembling will happen, just yellow, okay, and green particle, and yellow resembling. You can see that, okay, you can see that green is dark particles and yellows in the resemble particle, okay, and you can see they converge correctly after several several right here. Let's see, when the first time, second time, you see, converge. The yellow one, they resembling every iteration. Let's see. Great, that's the whole thing. You can understand the basis, the particle filter, how it's applied for the robots. Okay, you know they converge. The yellow ones resembling right now they converge and position around the robot, right? The position of robots. For the first time, you see. Okay.